everyone. Today is the second day of our ongoing course on matrix method of structural analysis. In the first lecture, we tried to understand the reason, a good reason for learning matrix method of structural analysis, and what are the limitations of the analysis procedure that we studied in our first course on structural analysis, and then how this course how that concept can be taken forward to solve, to analyze the structures that we come across in real life. Okay. And now this week and the next week we will be revisiting some of the basic concepts of structural analysis 1. So today we will start with degrees of freedom, constraints and static equilibrium. Okay. You see, what is degrees of freedom? As name suggests, it is the freedom of an object, right? How many, see, if we take an object, for instance, if we take a pen, this pen, any object in 3-dimensional space, this pen can move in this direction, this pen can move in this direction, this can move in this direction, and this pen rotates like this can pen rotate like this, and this pen can rotate like so. So these are the, so this pen has freedom to move in these three directions, and similarly this pen has freedom to rotate about this about 3 different axes. So this pen has 6 degrees of freedom. In fact, as in a 3-dimensional space, that is the maximum degrees of freedom any object can have. Okay. So degrees of freedom. So it is the freedom of an object to move. Now the degrees of freedom, if we have to define it, the definition goes like this: the degrees of freedom of a mechanical system is the number of independent coordinate required to completely specify the configuration of the system. Just now the definition that I gave and the definition written here, and you see there is a common link. These two definition actually tells you the same story. I leave it to you to realize that, and as we go further we'll understand this why this is what does it mean. Independent coordinate to required to completely specify the configuration of the system, right. So this is the degrees of freedom. Now you see what when you these are different degrees of freedom in 3 dimensions. Just now I showed you there are 3 translations, these translations, and then rotations about 3 axes. Now if we take a problem in 2D, then in 2 dimension we have 3 degrees of freedom. This axis is where the object lies in a plane. So you can have 2 translations and 1 rotation, 2 translation and 1 rotation. So these are these 3 degrees of freedom we have of an object in 2 dimension. Okay. Now let us see without support. Now what is support? You see, a structure is, as I said, a structure has freedom, or any object has freedom to move in 3-dimensional space, but we do not want our structure to move freely in 3-dimensional space, right. So we need to constrain some of its freedom, and that is done by providing supports. So what support does is, without providing any support, a structure is unstable. For instance, if we take a structure like this, there is no constraint. So it is a 2-dimensional object. So this object has 3 degrees of freedom. It can move in this direction, it can move in this direction, and it can rotate about this axis, right. So it can move in this direction, it can move in this direction, and it can rotate about this axis. So these are these 3 degrees of freedom it has. But now if we apply a load, then the structure becomes unstable. But we want our structure to be stable. We don't want our structure to move freely in space, and for that we need to constrain some of its degrees of freedom, and that is done through providing supports. So, what support exactly does is, if we same object, if we provide support, then if we apply a load like this, unlike the previous one, if we apply load here, this structure is not freely cannot freely move. So, it is support provides some of the constraints, support constrains some of the degrees of freedom, right. Now, now depending on the number of type of constraint, there are different kinds of support. Now, the thing is, in order to make a structure stable, we need to decide based on some again based on some conditions. Now, how many, in order to make a structure stable, how many degrees of freedom to be constrained, and depending on that, how many degrees of freedom to be constrained, we can have different kinds of supports, right. For instance, we have fixed support. Fixed support means this is the way we represent fixed support. You all are familiar with all this. These are some examples of fixed support. So, what happens in fixed support, the degrees of constraint are all degrees of freedoms are constrained. So, if this is a fixed support, this point cannot move at any in two-dimensional space. This can, any point can move in this direction and can rotate here, but since the support is fixed, it cannot move in any direction, right. Now, how constraint, how this freedom, how these degrees of freedom are constrained, support provides support reactions, right. So, what is the, if we have to draw the free body diagram of this support, if you recall, the free body diagram of a fixed support is, if this is the fixed support, the free body diagram is, then you have this force and a moment. So, this is the free body diagram of this support. So, this is, say, if this support is A, then this is A y, this is A x, and this is M A, right. These are the support A x, A y, A M A are the support reactions. If it is fixed support, we have 3 support reactions. Okay. Now, go next. If we have another support is the hinge support. Hinge support is represented like this. These are some examples of hinge support. So, as you can see here, this point cannot move in this direction and this direction, but this point has freedom to rotate. So, in this case, this support has only 1 degrees of freedom. Unlike previous case, in the fixed support case, there was no degrees of freedom. Degrees of freedom were 0. In this case, it has 1 degrees of freedom, and that degrees of freedom is the rotation. So, if I have to draw the free body diagram of this support, free body diagram. So, this is the support, and then this is the support reactions. We have only 2 support reactions. This is A y and this is A y, and this is A x. This is A x. There will be no moment here because rotation is not constrained. So, this is also we have seen. Now, next another support is roller support. As you can see here, the motion in this direction is constrained, but the displacement, the movement in this direction is allowed. So, it has rotation, degrees of freedoms are rotation and 1 translation. So, this can rotate about this and this can translate about this. So, what are the, if I have to draw the free body diagram of a roller support, the free body diagram will be only this. There will be, if this is A, then this will be, this is A y. There will be no horizontal reactions here because the horizontal movement is allowed. There will be no rotation here. There will be no moment here because rotation at this point is also allowed. So, these are different kinds of supports we can have. Similarly, in 3 dimension, the supports will be similar to this. It could be roller, it could be hinge support, it could be fixed support, but again if it is roller, then in which direction it is roller, in which direction the degrees of freedoms are constrained. If it is hinge, then which direction rotation is allowed. Depending on that, you can have different degrees of freedom at different supports. Okay, you can have a support in combinations of if you take any structure, then there will be many supports in the structure, and those support system can be the combination of different kinds of supports. Okay. Now, next is so what is free body diagram? Again, as I said, this is just we are reviewing the basic concept. If we take a simply supported beam which is subjected to concentrated load, suppose I want to draw the free body diagram of the entire system, then the free body diagram of the entire system will be, if it is hinge support, then hinge support, if it is roller support at B, roller support has one constraint, so there will be one reaction, suppose, and then hinge support has two constraint, two reaction, there will be no moment here, and suppose this is By and Ay and Ax are the support reactions at A. So, this is the free body diagram of the entire structure, and if I change the support condition instead of hinge, if we make it fixed support, then the free body diagram will be again for B it remains same, it is just only one reactions here, and since it is fixed support, there will be three reactions, two forces and one moment, and these are two forces and one moment, and these are the forces and moments, and this is the sign convention when I write moment as this. And remember, when we talk about sign convention is very much subjective. I am following this sign convention in this problem, but you may follow a different sign convention for your problem, but whatever sign convention you use, you be consistent with that sign convention. Okay. Now, similarly, if I take a section here at section Mn, and if I have to draw the free body, if we make this section and cut the entire structure into two parts, and then one part is this one is this part, another one is this part, and if we have to draw the free body diagram of these two, the free body diagram will be this part, free body diagram will be, these are the support reactions, and then these are internal forces. Since it is a beam problem, so we have three forces, one is axial force Fx, shear force Vx, and the moment Mx. These VFM are the internal forces, and similarly for this part of the structure, By is the support reactions, and similarly these are the internal forces. And remember, these internal forces for the equilibrium at this joint, this force and this force, the either side, both sides of the whatever forces you have on the either side of the section, they should balance each other. So, these Fx and Fx, they will cancel each other, Mx and Mx will cancel each other. That's the reason why these are shown in opposite direction, and similarly Vx, if it is downward here, it should be upward here, because they will cancel each other, and then only the equilibrium at section M will be maintained. Right. Now, okay, we can have, say, it is a truss problem. Similarly, if I have to draw the free body diagram of the entire structure, the free body diagram of the entire structure will be this. These are different members, and these are different, and then these are different, these are support, these are different members, and then we have these forces, this is force, and then we have another force P3 here, P3, so this is P3, P2, and then P1. And then we have support reaction at E, it is roller support. So, there will be one reaction only, which is EY, and then at A there will be two reactions, one is this direction, another one is this direction, this is AY and this is AX. So, this is the free body diagram of the entire system. Right. Now, if we take a section here, suppose one section here, and then we break the entire structure into pieces, then what will happen? And take different pieces, then we have to show the internal forces, right. These are since it is a truss problem, internal forces means, unlike beam where we had axial force, shear force and bending moment all, since it's a truss problem, every members are all members are 2 force members, and therefore the force only we have in the member is the axial force along the line of action, along the longitudinal axis of the truss. So these are the axial, these will be the internal forces in the member, right, and that also we have seen how to represent. These are the internal forces in the member. So if we draw the free body diagram of the entire system, the free body diagram will be something like this. These are the support reactions, and then F H y, this is the force in member H y. So again, this, when you are taking this section, if this force is this direction, for this section you have to show force in opposite direction, then only the equilibrium will be maintained, and that is true for all forces. So this is the free body diagram showing support reaction and internal forces, and similar free body diagram you can do for any structure, right. Now, so what is equilibrium? And the equilibrium is, so in the free body diagram just now what we have support reactions, we have external loads, and then we have internal forces, right. Now, equilibrium is when all these forces and the moments they cancel each other, they balance each other, the net force or the net moments in the structure is 0. So then only say this is in equilibrium, or to be specific, this, then we say that this object is in static equilibrium. This term is very important. This term is very important, static equilibrium. Whenever we talk about equilibrium in this course, it is understood, if it is not explicitly mentioned, it is understood it is static equilibrium. Okay. Now, the equilibrium is when external loads and the internal forces and moments developed in the structure are in equilibrium, and the equation for equilibriums are, this is the summation of external forces, summation of internal forces, that is equal to 0, and the summation of external forces, the support reactions are also included here, and the summation of external moments and internal moments about any point, any axis, they should also be 0. Now, if this philosophy has to be written in terms of mathematical equation, and these equations are this. These are called equations for static equilibrium. If you remember, in the previous class we show one is once a physical system, then idealization, and then writing the or representing the idealized system through some mathematical equation. These are the equations. These are one of those equations, equilibrium equations, static equilibrium equations, okay, for 3 dimensions and for 2 dimensions. 2 dimensions because there are two dimension 3 equations because there are 3 degrees of freedom, and 3 dimension 6 equation because there are 6 different ways, 6 independent way an object can move in 3 dimensional space. Okay. So, let us, what is determinate and indeterminate structure? Now, the determinate structure, as you have already we already know, the determinate structure is static. Again I will go back to that steps in engineering analysis. Once we write the mathematical equation, and then next part is to solve that mathematical expression, right. Now, the thing is if equilibrium equations are one part of those mathematical of that mathematical representation. Now, when we try to solve those equations, if the equilibrium equations alone are sufficient to have the solution of the idealized system, then we say the structure is determinate structure. Okay. And for instance, if we have a cantilever beam which is subjected to, say, uniformly distributed load, and then this is A, this is B, and if we write the free body diagram of the entire beam, this is A, this is AY, and this is AX, horizontal reaction, and then we have moment MA, and then there is, and then on top of that we have external load. We have external load like this, say this is W, So, this is W. Now, once we have this, now write summation of f x is equal to, so we have three unknowns here, a x, a y, a x, summation of f x is equal to 0 if we write, f x is equal to 0 if we write, then this gives us a x is equal to 0, a x is equal to 0, right. Directly this gives you a x is equal to 0. If you write summation of f y is equal to 0, if y is equal to 0, then a y we get, if this length is L, a y will get W into L, and if we get summation of say m a is equal to 0, moment about a is equal to 0, and this gives us m a is equal to W L square by 2, right. So, we have so three equations, three unknown, and all these equations are equilibrium equations, and for this structure these are called determinate structure. For any structure if it can be done, these structures are determinate structure. But you know, many structure, or rather I would say most of the structure that we come across, those structures are not determinate structure, because equilibrium equations alone cannot give you the solution of those structure, and those structures are called indeterminate. So, this is the example that I showed. Those structures are called indeterminate structure. Indeterminate structure is only static equilibrium, static equation alone are not sufficient to determine the support reactions and internal forces. And for instance, if we have the same example, but cantilever beam, but make it another support here. So, it is subjected to again uniformly distributed load. Now, what are the unknown? If we draw the free body diagram, this is A, this is B. So, we have A x, A y, and then just A x, and then moment m a, and then here also we have B y, right, B y. So, number of unknowns, we have number of unknowns 4, one is 1, this is 1, and then 2, 3, and then 4. Number of unknowns are 4. What are the, how many equations we have? We have only 3 equations. Summation of f x is equal to 0, summation of f y is equal to 0, and moment is equal to summation of say moment about any axis, say about any axis will be 0. Only 3 equations we have. So, here we cannot solve the entire system by only these 3 equilibrium equations. So, in that case what we need is, we need an additional equation. We need an additional equation. And if you remember when you solve indeterminate structure, you studied compatibility equation. Again I will go back to that flow there. If you remember, go back to the first class, we wrote equilibrium equations, compatibility equations, and boundary conditions. Equilibrium equations only first determinate structure, equilibrium equations plus compatibility equations or some other equations. We will see what those equations are, and along with the boundary conditions, right. So, for those structures are called indeterminate structure. Now, so we have based on the how many equations are available and how many unknowns are present in our analysis, we can have three different cases. One case is when your number of unknowns less than the number of equilibrium equations, and another case is when your number of unknowns are exactly equal to the number of equilibrium equations, and number of unknowns are greater than the number of equilibrium equations. In the first case, is the second one is determinate structure, because your number of unknowns are same as equilibrium equations. So, equilibrium equation can be used alone to solve the number of total unknown. And then second, if the number of unknowns are greater than number of equilibrium equations, so we need additional equation. Without that additional equation, the structure cannot be analyzed. And then the first one, the physical interpretation of that is if the number of unknowns are less than equilibrium equation, the physical interpretation is the structure becomes unstable. You see here, your unknowns are only two unknowns, vertical reactions here, but the equations are available is three equations are available, summation of forces in vertical direction, summation of forces in horizontal direction, and summation of moments are 0. So, this is unknown. This is this is an unstable case, right. So, what we do next is we will see once we have understood what is or rather once we have revisited what is indeterminate structure and what is determinate structure, the next question comes is how to quantify the indeterminacy of a structure, right. If it is determinate, then it is very straightforward. You have an equilibrium equation exactly same as the number of unknown and solve it. But if in case of indeterminate structure, where your number of equations are number of unknowns are more than the number of equations, then the question comes is how many additional equations are available, how many additional equations are required. So, we need to quantify the indeterminacy of the structure. So, next class what we do, we will see how to determine indeterminacy of a structure. Two kinds of indeterminacy, one is static indeterminacy and kinematic indeterminacy. Okay, then we stop here. See you in the next class.